In previous videos, we saw that there exists a duality between particles and waves. It was Einstein who first proposed that light, which was known to be a wave, also has a particle-like nature. Around 2 decades later, de Broglie proposed that electrons, which were known to be particles, also have a wave-like nature. Schrodinger then developed a wave equation for the electron that successfully described the electron energy levels in hydrogen. So we see that waves can be particle-like and particles can be wave-like. We can extend this insight to systems that consist of multiple particles. Bose showed that Planck's blackbody radiation law could be derived by assuming that light consists of particles, or photons, which are fundamentally indistinguishable. Dirac mathematically described electromagnetic fields as a system of indistinguishable particles via a method that became known as second quantization. With this new theory, he could explain stimulated emission, spontaneous emission, and the quantum dispersion formula originally derived by Kramers and Heisenberg. So we see that a wave field can be described as a system of multiple indistinguishable particles. Then, by the logic of the wave-particle duality, one can wonder whether a system of multiple indistinguishable particles, such as electrons, can be described as a wave field. This is the core idea of quantum field theory, the fundamentals of which were developed mainly by Jordan, Heisenberg, and Pauli. In this video, we will see how we can apply quantization rules to classical wave fields. With this new theory, we will revisit the Klein-Gordon equation. This equation had previously been discarded as a failed attempt at a relativistic quantum theory of the electron. Lastly, we will apply the new theory of field quantization to the Maxwell equations that describe electromagnetic radiation. This yields a coherent theoretical description of light that accounts for both its wave nature and its particle nature. Quantum field theory thus provides some sort of resolution to the paradox that Einstein had introduced at the very start of the quantum revolution. To better understand the reasoning behind quantum field theory, let's outline the historical context of its development in relation to previous videos. Dirac proposed his theory of second quantization, which treats radiation as a system of multiple indistinguishable particles, in 1927. 1 year later, he proposed a relativistic theory of the electron. The Dirac equation correctly predicts the fine structure of the electron energy levels in hydrogen, since this equation accounts for both the relativistic energy corrections as well as the electron spin. This was a tremendous achievement, but the equation predicted the existence of infinitely many negative energy levels, which seemed unphysical. To explain this result, Dirac boldly proposed that those negative energy levels are filled with an infinite sea of electrons, which became known as the Dirac sea. Because the electrons should satisfy Pauli's exclusion principle, the Dirac sea prevents that positive energy electrons can transition into the already occupied negative energy states. Dirac then predicted that when a negative energy electron is excited to a positive energy level, it leaves a hole in the Dirac sea, and this hole would appear to us as a positively charged particle. Dirac first thought that this particle would be a proton, but it was pointed out that the new particle should have the same properties as the electron, except for its charge. So Dirac proposed instead the existence of a new, still unobserved particle, the anti-electron or positron. At first this seemed like an outlandish idea, but when the positron was experimentally observed a year later, it was clear that this strange theory had to be taken seriously. The development of quantum field theory was closely intertwined with all these other advancements. Already in the paper where matrix mechanics was being developed, Jordan attempted to quantize fields by treating them as systems of coupled harmonic oscillators. After Dirac had developed his theory of second quantization, Jordan and Oscar Klein demonstrated that equivalent results could be obtained by quantizing wave fields. Heisenberg and Pauli formulated a coherent theory of field quantization via the methods of Lagrangian and Hamiltonian mechanics, the same methods that had been used to develop Heisenberg's matrix mechanics and Schrödinger's wave mechanics. When the existence of positrons was accepted, Pauli and Pauli-Weisskopf used field quantization to provide an alternative interpretation to Dirac's theory of holes in the Dirac sea. Pauli even described this new theory as the anti-Dirac theory. To understand how we can quantize the motion of fields, let's recap how we quantize the motion of particles, which is known as the first quantization. We first describe the classical motion of the particle with Hamiltonian mechanics, where we define the conjugate variables for position and momentum. To quantize the particle's motion, we promote the conjugate variables to linear operators that satisfy the canonical commutation relation. Therefore, if we want to quantize fields, it stands to reason that we should first describe their motion using Hamiltonian mechanics and then impose the canonical commutation relation to conjugate field variables. So to understand how fields can be described with Hamiltonian mechanics, let's also first recap how Hamiltonian mechanics works for particles. The starting point is the idea that we can describe a particle's motion by solving a minimization problem. This is inspired by Fermat's principle from optics, which states that light refracts in such a way that its travel time is minimized. In other words, one can derive Snell's law of refraction by minimizing the travel time of light. One can similarly ask whether Newton's second law for a particle can be derived by minimizing some quantity. Using the analogy with Snell's law and Fermat's principle, one can infer that to describe a particle's motion, we should minimize a quantity called the action, which is found by integrating a quantity called the Lagrangian over time. For the simple case of a particle moving in a fixed potential, the Lagrangian is given by the kinetic energy minus the potential energy. This minimization principle is called Hamilton's principle of least action. This minimization problem is solved by the Euler-Lagrange equation. By comparing the Euler-Lagrange equation to Newton's second law, one can define a generalized force and a generalized momentum. The generalized momentum and the generalized position coordinate together form a pair of conjugate variables. By applying a Legendre transform, we find the Hamiltonian, and we find the Hamiltonian equations of motion that a pair of conjugate variables must satisfy. For the simple case of a particle moving in a fixed potential, the Hamiltonian is the total energy. So while the Lagrangian is given by the kinetic energy minus the potential energy, the Hamiltonian is given by the kinetic energy plus the potential energy. Now that we have recapped the basics of Lagrangian and Hamiltonian mechanics for particles, we can apply these insights to describe the dynamics of fields. In Lagrangian mechanics for a particle, we define the particle's starting location at some starting time, and we define the particle's location at some ending time. For each path that connects the starting point to the end point, we calculate the Lagrangian. Similarly, when we consider fields, we can define the field's starting configuration at some starting time, and we define the field's ending configuration at some ending time. For each way that the field can transition from the starting configuration to the ending configuration, we can calculate the Lagrangian. Of all the possible paths that we can define for the particle, the path that the particle will actually take is the one for which the action is minimal. Similarly, of all the ways that the field can transition between configurations, the way that the field will actually evolve in time is the way for which the action is minimal. To minimize the action, we set up the Euler-Lagrange equation. From the Euler-Lagrange equation, we can define the conjugate momentum. When we consider the dynamics of fields, the momentum variable is a function of both space and time, and it is conjugate to the field variable. We know from special relativity that the field at one position cannot instantaneously affect the field at another position some distance away. This is because information can travel no faster than the speed of light. This puts a constraint on the form that the Lagrangian of a field can take. Specifically, it means that at each point in space, we can define a Lagrangian density, whose value only depends on the field and its derivative at that point. To find the Lagrangian, we integrate the Lagrangian density over space. Since the action is an integral of the Lagrangian over time, and the Lagrangian is an integral of the Lagrangian density over space, the action is an integral of the Lagrangian density over space-time. So for particles, we define a Lagrangian that depends on the particle's position and its velocity. For fields, we define a Lagrangian density that depends on the field configuration and its time derivative, but in addition, it also depends on the field's spatial derivative. So when we compare the Euler-Lagrange equation for particles to the Euler-Lagrange equation for fields, we find that the latter contains an extra term for the spatial derivative of the field. For a particle, we could define a generalized momentum and generalized force by comparing the Euler-Lagrange equation to Newton's second law. Similarly, in the Euler-Lagrange equation for fields, we can relate the term with the time derivative to the field momentum. This means that the term with the spatial derivative is related to a force. This makes sense when we think, for example, of waves on a string. At each point of the string, the momentum is related to how fast that point moves up or down, while the force that acts on that point is related to the gradient of the string. So for a particle, we define the generalized momentum as the partial derivative of the Lagrangian with respect to the particle's velocity. And for a field, we define the generalized momentum as the partial derivative of the Lagrangian density with respect to the time derivative of the field. It is common to perform these calculations with relativistic notation, which we've discussed in a previous video. This notation uses 4 vectors, where the 0th entry corresponds to time, and the following 3 entries correspond to the 3 spatial dimensions. We also use Einstein notation, where we sum over repeated indices. So when we write the action as an integral of the Lagrangian density over both space and time, we can write all the derivatives of the field as a 4 gradient, and we integrate over all components of the 4-dimensional spacetime coordinate vector. The Euler-Lagrange equation contains the sum of derivatives with respect to all coordinates, so that can be written compactly by using Einstein notation. To see how Lagrangian mechanics works for fields, let's look at a wave field as an example. In this case, we know that the field should satisfy the wave equation. We can write this equation with relativistic notation, where we use the Einstein summation convention to write the temporal and spatial derivatives more compactly. We know that this wave equation should follow from the Euler-Lagrange equation, which we can also write more compactly with relativistic notation. By comparing the Euler-Lagrange equation to the wave equation, we can infer the expression for the Lagrangian density. Also, this Lagrangian density we can write in relativistic notation. From the Lagrangian density, we can calculate the momentum that is conjugate to the field. We can write the momentum in terms of the 0th component of the 4 gradient, which contains the time derivative. The expression can be simplified if we choose the units where the speed of light equals 1. Now that we know the Lagrangian density, we can calculate the Hamiltonian density by applying the Legendre transform. We plug in the expressions for the momentum and the Lagrangian density. We can choose to write the Hamiltonian density in terms of the momentum. Note the similarity to the case of a particle, where the Lagrangian is the kinetic energy minus the potential energy, while the Hamiltonian is the kinetic energy plus the potential energy. However, the energy term for the case of fields isn't exactly the potential energy, but rather the gradient energy. With these results, we can demonstrate that the dynamics of the field can be described with Hamilton's equations of motion, in close analogy to the case of particles. First, we define the Hamiltonian as the integral of the Hamiltonian density, similar to how we define the Lagrangian as the integral of the Lagrangian density. This means that the Hamiltonian is not a function, but a functional, which is indicated by the straight brackets. That is, it takes in a function as an argument, and then converts the entire function to an output, which is a scalar. This is in contrast to the Hamiltonian density, which is a normal function of the field and the momentum. It takes in only a single value of the field as its argument, rather than the entire function. We can plug in the expression for the Hamiltonian density. The reason why the distinction between a functional and a function is so important is because when we take the derivative of the Hamiltonian with respect to the momentum, it is a functional derivative. The functional derivative is defined as follows. If we change the entire input function by adding another small function to it, then the functional will change by a small amount. The functional derivative is defined such that this change in the functional is given by the integral of the functional derivative times the change of the input function. We can calculate the functional derivative for this particular case by changing the momentum function by a small function. We can calculate by how much the integrand changes and then integrate this change to find the change in the functional. By comparing this expression to the definition of the functional derivative, we find the expression for the functional derivative. In this case, we could have found the same result more straightforwardly by directly taking the derivative of the Hamiltonian density with respect to the momentum. But we will see that the calculation is less straightforward when we take the functional derivative with respect to the field. We again recall the definition of the functional derivative. Note that when we change a function by adding a small function to it, then the derivative of the function changes by the derivative of the small function. So to calculate the change in the functional, we integrate the derivative of the Hamiltonian density with respect to the field spatial derivative, multiplied by the change in the derivative. To rewrite this expression in a way such that we can compare it to the definition of the functional derivative, we integrate by parts. We integrate one factor and take the derivative of the other. We assume that the field vanishes at infinity, so that only the term with the integral remains. When we compare the resulting expression to the definition of the functional derivative, we find an expression for the functional derivative of the Hamiltonian with respect to the field. Note that this result cannot be found trivially by taking the derivative of the Hamiltonian density with respect to the field. With these results, we can verify that the Hamiltonian equations of motion hold. We find that from the second equation we find the definition for the momentum. When we plug this result into the first Hamiltonian equation of motion, we recover the wave equation. Therefore, we confirm that the Lagrangian and Hamiltonian formalisms for fields work in a very similar way as they do for particles. Now that we know how the dynamics of fields can be described with Lagrangian and Hamiltonian mechanics, we can quantize them according to the familiar procedure from Heisenberg's matrix mechanics. In matrix mechanics, we saw that to quantize the dynamics of a particle, we require that the conjugate position and momentum variables satisfy the canonical commutation relation. So similarly, we can enforce this commutation relation to the conjugate field and momentum variables. We now have an operator, indicated by a hat, for each point in space. The operators are a function of time, just like in the Heisenberg picture for quantum mechanics of a particle. The commutation relation holds only when we consider the field and momentum operators at the same point in space at the same time. If we consider two different points in space at the same time, then the operators commute. That is, they act like normal classical variables, rather than quantum variables which obey an uncertainty relation. This means that if we measure a field at one point in space, it cannot instantaneously affect the field at another point in space, because that would violate the principle of causality that follows from special relativity. Now that we have quantized the field with the Heisenberg picture, we can briefly look at what this means in the Schrodinger picture. In the case of a classical particle, we can assign to it a certain position. When we quantize the particle in the Schrodinger picture, the particle does not have a definite position anymore, but rather it is described by a Schrodinger wave function. This wave function takes as input argument a certain value for the position, and then it returns a complex valued number. The squared modulus of that complex valued number indicates the probability density to find the particle at that position when it is measured. If we consider a classical field, then the field is in a certain configuration, where each point in space has a definite field value. When we quantize the field in the Schrodinger picture, the field does not have a definite distribution in space anymore, but rather it is described by a Schrodinger functional. This functional takes as input an entire field distribution, and then it returns a complex valued number whose squared modulus indicates the probability that the field has a certain spatial distribution. However, in the following, we will continue to work in the Heisenberg picture, where we assign to each point in space a time-dependent operator. We will now rederive the theory of second quantization, starting from the Hamiltonian that we found for a field satisfying the wave equation. At this point, all the quantities are still classical. We can write the field and momentum functions as a sum of plane waves, whose weights are given by the Fourier transforms of the field and momentum. It follows from Parsifal's theorem that in the integral we can change the squares of the real valued functions with the squared modulus of their Fourier transforms. Taking the spatial derivative of a function means multiplying its Fourier transform with the spatial frequency. From the resulting integral, we find an expression for the energy contained by a single spatial frequency. So far, the calculation only involved purely classical quantities. We will now incorporate the quantum mechanical aspect by considering the commutation relation of the field operators. In particular, we will see what the commutation relation for the Fourier transformed fields look like. We plug in the definition for the Fourier transformed fields. We use the commutation relation for the field operators. We use the delta function to integrate away one of the variables. The resulting integral reduces to a delta function. We have found the commutation relation for the Fourier transformed field functions. The canonical commutation relation only applies when we consider the field and the momentum for spatial frequencies with opposite sign. If we consider any other combination of spatial frequencies, the field and momentum operators commute, as if they were classical functions. So we found the expression for the energy per Fourier component of the field, and we found the commutation relation for the Fourier transformed field operators. Since we assume that the field is real valued, the complex conjugate of a Fourier coefficient equals the Fourier coefficient of the negative spatial frequency. We use this fact to rewrite the squared modulus of the Fourier transform function. We can now apply insights from the quantum harmonic oscillator to rederive the theory of second quantization. We define the ladder operator as the field operator plus or minus I times the momentum operator. We can calculate the product of the two operators and the product in reversed order. We take the difference of the two products to calculate the commutator of the ladder operators. The quadratic terms cancel out, and the difference of the cross terms reduces to two commutators of the field and momentum operators. When we plug in the canonical commutation relation, we find that the commutator of the ladder operators is equal to -1. This is consistent with the result of the quantum harmonic oscillator. We can also calculate the sum of the two products of ladder operators. We recognize that the quadratic terms correspond to the Hamiltonian density. But in addition, we also have the cross terms. We will show that when we integrate over all frequencies to find the total Hamiltonian, these terms cancel. First note that we can simplify the prefactor, so it doesn't depend on the spatial frequency k. If we then integrate these terms over all spatial frequencies k, we observe that the integrand is an antisymmetric function. That is, if we flip the sign of the spatial frequency, then the value of the integrand changes sign. So when we integrate over all spatial frequencies, then the contributions from the positive spatial frequencies cancel out with the contributions from the negative spatial frequencies, and so the total integral vanishes. Therefore, when we integrate the Hamiltonian density to find the total Hamiltonian, we can plug in the sum of the products of the ladder operators. We can rewrite one product in terms of the commutator of the ladder operators, which we know reduces to 1. We find that the energy operator per spatial frequency can be written in terms of creation and annihilation operators. It implies that the energy of each spatial frequency consists of a zero-point energy, which is 1/2 the photon energy, plus the number of photons times the photon energy. In this theory of quantized fields, we can interpret the introduction of creation and annihilation operators as the separation of positive and negative frequencies. This can be shown as follows. When we write the field as a sum of plane waves with time-dependent coefficients, then each coefficient can be written as the sum of complex exponentials, where the angular frequencies depend on the spatial frequency, and the sign can be either positive or negative. Because we assume the field to be real-valued, the Fourier coefficient for a spatial frequency -k must be the complex conjugate of the coefficient for spatial frequency k. The momentum is given by the time derivative of the field. Therefore, we can find its Fourier coefficient by taking the time derivative of the Fourier coefficients of the field. Now we recall the definitions of the creation and annihilation operators. When we plug in the expressions for the Fourier coefficients, we find that the annihilation operator corresponds to the negative frequency, and the creation operator corresponds to the positive frequency. The annihilation operator for the same spatial frequency with opposite sign corresponds to the other coefficient, and similarly for the creation operator. Therefore, we can express the Fourier coefficient of the field as the sum of the annihilation and creation operators for spatial frequencies with opposite sign. The Fourier coefficient of the momentum can be expressed as the difference of the annihilation and creation operators. This result allows us to express the Fourier expansion of the field in terms of creation and annihilation operators. If we want the integrand to contain only creation and annihilation operators of the same spatial frequency, then we can split the integral, change the sign of the spatial frequency in one of them, and then combine the integrals again. Therefore, to quantize a real-valued field, we can write down its Fourier transform in this form, and then substitute the coefficients with properly weighted creation and annihilation operators. We can quantize the momentum function in a similar way. Now that we know how to quantize fields, let's revisit the Klein-Gordon equation and see how it is made relevant again by quantum field theory. Let's first recall what the Klein-Gordon equation is and why it was rejected initially. The Klein-Gordon equation was proposed as a relativistic version of the Schrodinger equation. It is obtained by considering the relativistic equation that relates energy and momentum, and then substituting the energy and momentum with differential operators, as is done to obtain the Schrodinger equation. This results in a quantum wave equation that is consistent with special relativity. Even though this equation is named after Oskar Klein and Walter Gordon, it was already considered by Schrodinger himself, even before he published his non-relativistic Schrodinger equation. The reason why he didn't pursue this relativistic wave equation was because it gave the wrong corrections to the hydrogen energy levels. It was already known from Sommerfeld's old quantum theory that the relativistic energy levels of hydrogen are described by integer quantum numbers, but the Klein-Gordon equation yields a formula for the energy levels that involves half integers. It was later found that this mismatch was caused by the fact that the electron spin was not taken into account. Sommerfeld's formula ignored both the wave nature of the electron and the electron spin, and these two errors happened to conspire in such a way that a correct formula accidentally emerged. And so one could believe that the Klein-Gordon equation was essentially the correct way to incorporate relativity, but something needed to be added to include the effects of electron spin. However, Dirac had more fundamental objections to the Klein-Gordon equation. In the Schrodinger equation, the squared modulus of the wave function could be interpreted as a probability density, because it is positive everywhere and its integral over space is always constant in time. However, for the Klein-Gordon equation, the quantity whose integral is constant in time is not always guaranteed to be positive everywhere. But then we cannot interpret it as a probability density, because probabilities must always be positive. Fundamentally, this was caused by the fact that the Klein-Gordon equation contained a second-order time derivative, while the Schrodinger equation contained only a first-order time derivative. To Dirac, it was essential that a quantum wave function can be interpreted as a probability amplitude, so he set out to find a relativistic wave equation that contained only a first-order time derivative. The only way he managed to obtain this was to abandon the notion of a scalar wave function, and to instead introduce a four-dimensional vector of wave functions. It turned out that these extra components of the vector accounted for the spin of the electron, even though this was not Dirac's initial goal. Therefore, the Dirac equation correctly described the hydrogen energy levels, since it accounted for both relativity and electron spin. But the great success of this equation also raised more questions. Electron spin was usually described by a two-dimensional vector. So why does the Dirac equation require a four-dimensional vector? What is the significance of these two extra wave functions? Moreover, the Dirac equation still had infinitely many negative energy states, just like the Klein-Gordon equation. If these energy states indeed existed, why would an electron not continually drop down to lower and lower energy levels, each time emitting energy in the form of photons? Dirac proposed that all these negative energy levels are already occupied by an infinite sea of electrons. Then, due to Pauli's exclusion principle, other electrons cannot drop down to these lower energy levels. If an electron was excited from a negative energy state to a positive energy state, it would leave a hole in the sea of electrons, and this hole would act as another particle. That particle is then described by the extra two wave functions that occur in the Dirac equation. Dirac proposed that this particle corresponding to this hole would be the proton, but it soon became apparent that this could not be the case. So instead, Dirac proposed the existence of an entirely new sort of particle, which he called the anti-electron, and which is now known as the positron. The idea of an infinite sea of electrons and an entirely new kind of particle seemed suspicious to many scientists, but after the positron had been observed experimentally by Carl Anderson, these strange ideas of Dirac had to be contended with seriously. This is where the arguments of Wolfgang Pauli and Victor Weisskopf come in. Now taking seriously the concept of antimatter that was predicted by Dirac's theory of holes, they proposed an alternative theoretical description that avoids the introduction of an infinite sea of electrons. In this theory, they reconsidered the Klein-Gordon equation. Since that equation had been discarded some time ago and been replaced by the more successful Dirac equation, Pauli and Weisskopf must first argue why the objections against the Klein-Gordon equation were not valid. They first note that Dirac's theory of holes and the experimental discovery of antimatter imply that a relativistic quantum theory must necessarily be a theory of multiple particles. The existence of an electron is tied to the existence of a hole or positron, and therefore a fully correct quantum theory cannot describe a single electron in isolation. It must necessarily take the existence of the other particles into account. Once we accept that a correct theory must be a many-particle theory, then we can no longer insist that there must be a quantum wave function that describes the probability distribution of a single particle. This was Dirac's original reason to reject the Klein-Gordon equation, but now it must be considered invalid. Instead, the quantity that is conserved is not the total probability of a single particle, but rather the total electric charge of many particles. When an electron-positron pair is created, or when an electron and a positron annihilate, then the number of particles changes, but the total electric charge is conserved. So if the conserved quantity is not probability but charge, then there is no problem with the fact that the density of this quantity can be negative. It's a problem if we have a negative probability density, but there is no problem at all if we have a negative charge density. Therefore, all the objections to the Klein-Gordon equation vanish once we make it a many-particle theory. And we already saw that we could describe systems of many particles by quantizing fields. Therefore, we will demonstrate that when we treat the Klein-Gordon equation as a quantum field, we can reproduce the prediction of antimatter without resorting to Dirac's idea of holes in an infinite sea of particles. For this reason, Pauli even described this theory as the anti-Dirac theory. So far, we have quantized a real-valued field that satisfies the wave equation. In the following, we will see that quantum field theory predicts the existence of antiparticles when we consider complex-valued fields. To give a quick impression of how this works, we note that making the field complex-valued introduces an extra degree of freedom. This extra degree of freedom corresponds to a new type of particle, which is the antiparticle. There are various ways to understand how a complex-valued field introduces a new degree of freedom. For example, we can write the field as a linear combination of its real part and its imaginary part, which are independent real-valued fields. Also, when we take derivatives of complex valued functions using Schrodinger derivatives, then the complex variable and its complex conjugate are treated as two independent variables. The third way to see how a complex valued field introduces an extra degree of freedom is by looking at its Fourier transform. For a real valued function, the Fourier coefficients of the negative spatial frequencies are given by the complex conjugate of the Fourier coefficients for the positive spatial frequencies. We saw that to quantize the field, we separate the positive and negative frequencies and substitute the coefficients with creation and annihilation operators. But for a complex valued field, the Fourier coefficients for positive and negative frequencies are independent of each other. So in quantizing the fields, we will see that we introduce creation and annihilation operators for different particles. To understand in more detail how to quantize the complex valued Klein-Gordon field, we first find its Lagrangian density. Recall how for the real valued wave equation, we use the Euler-Lagrange equation to find the Lagrangian density. The Klein-Gordon equation is basically the same as the wave equation, except it has an additional mass term. We have a complex valued field, and according to the theory of Schrodinger derivatives, a complex variable and its complex conjugate are treated independently. So the complex conjugate of the field also satisfies the Klein-Gordon equation, and it can also be plugged into the Euler-Lagrange equations as an independent variable. From this we infer the Klein-Gordon Lagrangian density for a complex valued field. Note how the first two terms reduce to the Lagrangian density of the real valued wave equation if the field is assumed to be real valued. The next important point that we will discuss is Noether's theorem. This theorem describes how symmetries in the Lagrangian density correspond to conserved quantities. The reason why this theorem is relevant for understanding the complex Klein-Gordon field is because conserved quantities were a key point in Pauli's and Weisskopf's argumentation. The total number of particles is not conserved, but the total charge is. Suppose we have a Lagrangian density that depends on the field and its derivatives. We apply some change to the field, and as a consequence, the spatial derivative changes, and so does the time derivative. To calculate the resulting change in the Lagrangian density, we apply the chain rule. We can rewrite the term containing the spatial derivative by using the product rule, and we can do the same for the term containing the time derivative. To consider a case that is physically relevant, we assume that the original field satisfies the Euler-Lagrange equation. By substituting this result in the expression for the change in the Lagrangian density, we can cancel three terms, and thus simplify the expression significantly. Now we can compare this expression to the equations that conserved quantities satisfy. The density of a conserved quantity must satisfy the continuity equation. This equation says that if we consider a small volume, then the divergence of the currents determines the rate at which the density decreases. Basically, it means that the density cannot be created or destroyed, but only flow around. Therefore, if we integrate the density over all space, the result must be constant in time. Now we assume that the Lagrangian density does not change when we change the field in a specific way. We say that the Lagrangian density has a certain symmetry, because something is symmetric when it remains unchanged under a certain transformation. In this case, we can rearrange the expression for the change in the Lagrangian density, and we find that it has the same form as a one-dimensional continuity equation. By comparing the expressions, we can identify the Noether charge density, whose integral is a conserved quantity, and the Noether current. These are the results for a real valued field. For a complex valued field, the expression for the change in the Lagrangian density obtains extra terms due to the derivatives with respect to the complex conjugate of the field, and as a consequence, the Noether charge density and current also get extra terms. Now that we know how to calculate conserved quantities from symmetries in the Lagrangian density, let's consider the complex valued Klein-Gordon Lagrangian density and see what symmetries are present. We see that if we multiply the field with the global phase factor, then it cancels out with its complex conjugate. To apply Noether's theorem, we need to change this multiplication into an addition to the field. We do this by considering an arbitrarily small phase shift and Taylor expanding the complex exponential. We then find the terms that are added to the field and its conjugate. Plugging this into the formulas we found, we immediately find the Noether charge density and the Noether current. The charge density we found is the same expression that we considered previously, and which Dirac said it couldn't be interpreted as a probability density because it's not always positive. Now let's revisit the derivation of the Noether charge and current. We calculated the change in the Lagrangian density as a consequence of a change in the field and assumed that this change is zero. From this we find an expression that resembles the continuity equation. However, our requirement that the change in Lagrangian density must be zero is too stringent. If instead we set it equal to the sum of some time derivative and some spatial derivative, then we still obtain an expression that resembles the continuity equation, where the charge density and current now contain an extra term. With this updated result, let's look again at the Klein-Gordon Lagrangian density. We consider the transformation where the field is slightly shifted in time. To convert this change to an addition to the original field, we apply a first-order Taylor expansion. From this we find the change in the field. The change in the Lagrangian density can also be found by taking its time derivative. We can compare this expression to the result we found previously, and from this we can calculate the Noether charge density. We find that it is equal to the Legendre transform of the Lagrangian density, which yields the Hamiltonian density. Therefore, by considering translations in time, we find that the total energy is conserved. We also find the corresponding Noether current. For the final conserved quantity that we consider, we shift the field in space. To find the change in the field, we apply a first-order Taylor expansion. We compare it to our previous result and then write down the Noether charge and the Noether current. So we found three conserved quantities. One conserved quantity followed from global phase symmetry. Conservation of total energy followed from considering time translations, and the last conserved quantity, which followed from space translations, corresponds to the total momentum. This can be verified by comparing its dimensions to the dimensions of energy. From the Klein-Gordon Lagrangian density, we can define the conjugate momenta, and we can write the conserved quantities in terms of these momenta. With Parsifal's theorem, we can change the integrals over space into integrals over spatial frequencies. That is, we change the fields and their momenta into their Fourier transforms. We can rewrite the energy integral by collecting terms and defining a new parameter kappa. To understand further what these expressions imply, we investigate what happens when we split the complex Klein-Gordon equation in its real part and its imaginary part. This allows us to reuse the results we found for the real valued wave equation and apply it to the complex valued Klein-Gordon field. We saw that from the Lagrangian density, it follows that both the field and its complex conjugate satisfy the Klein-Gordon equation. Now we write the field as its real part plus I times its imaginary part. If we plug these expressions in the Lagrangian density, we find that the Lagrangian density can be written as the sum of a Klein-Gordon Lagrangian density for the real part and a Klein-Gordon Lagrangian density for the imaginary part. It follows that both the real part and the imaginary part satisfy the Klein-Gordon equation. We now recall the result that we obtained for quantizing real-valued fields, where we substituted the Fourier coefficients with creation and annihilation operators. In this case, the real part and imaginary part each have their own pair of creation and annihilation operators. The result for the real-valued Klein-Gordon equation is the same as the result for the real-valued wave equation, except that the angular frequency is now proportional to the new parameter kappa instead of the spatial frequency k. This is because of the extra mass term that is present in the Klein-Gordon equation, but which is not part of the wave equation. We also need to express the conjugate momenta in terms of their real part and imaginary part. To see how we should apply this decomposition, we recall that the complex valued field and momentum must satisfy the equal time commutation relation. If we choose signs for the momenta that are opposite to those for the fields, we can verify that the correct commutation relation holds. We can write the complex valued field in terms of the creation and annihilation operators of the real and imaginary parts. When we collect the creation operators together, we can define new creation and annihilation operators that are linear combinations of the creation and annihilation operators of the real and imaginary part. Similarly, we can write the complex conjugate of the field in terms of the real part and imaginary part, collect the creation operators, and write the fields in terms of the newly defined creation and annihilation operators. To verify that these newly defined operators are themselves proper creation and annihilation operators, we check that they satisfy the expected commutation relation. When we calculate the commutator of the first pair of creation and annihilation operators, we find that it is equal to 1, as should be the case. For the second pair, we find the same result. The commutator of the creation operator from one pair and the annihilation operator from the other pair vanishes. This indicates that each pair of operators refers to a distinct kind of particle. Now we find the expression for the quantized momenta. Like before, we take the linear combination of the real and imaginary parts, collect the creation operators, and express the result in terms of the newly defined creation and annihilation operators. To express the complex conjugate of the momentum in terms of the new operators, we repeat the same procedure. We now have obtained all the results necessary to interpret the conserved quantities that we found via Noether's theorem. The first quantity we consider is the total energy. We write the field and momentum in terms of their real and imaginary parts. We find that the total energy is given by the sum of the energy of the real part and the energy of the imaginary part. We recall from the quantization of real-valued fields that we can write the energy in terms of the creation and annihilation operators, where the angular frequency omega now depends on the mass term of the Klein-Gordon equation. We find that the sum of the number operators of the real and imaginary parts equals the sum of the newly defined number operators. Now we consider the next conserved quantity, which is the total momentum. We again write the fields in terms of their real and imaginary parts. When we expand the products, we find that all the cross terms cancel. The resulting expression is the sum of the momentum of the real part and the momentum of the imaginary part. We will calculate for now only the real part, and after that apply the result to the imaginary part as well. We plug in the Fourier expansions we found for the field and momentum operators. We expand the product, and then integrate over space to reduce the complex exponentials to delta functions. If we then integrate over one of the spatial frequencies, we can substitute it with the other spatial frequency, thanks to the delta functions. The resulting expression we can rewrite further by splitting the terms in two groups. we note that the integrand of the second integral is an antisymmetric function. That is, if the argument changes sign, then the function value changes sign. So if we integrate this function, the contributions from the negative spatial frequencies cancel with the contributions from the positive spatial frequencies, and the integral vanishes. The remaining integral tells us that the total momentum equals the number of particles times the momentum h bar k of each particle. When we add the contributions from the real part and imaginary part together, we can again introduce the new creation and annihilation operators. Now we look at the final conserved quantity, which is due to the global phase symmetry. Note that this symmetry is unique to the complex-valued Klein-Gordon field. The total energy and total momentum are also for real-valued field conserved quantities, which is why we could just add the energy or momentum of the real and imaginary parts to find the total energy or momentum. But for this new conserved quantity, it's not possible to find a similar conserved quantity for the real and imaginary parts separately. So instead of writing the field and momentum in terms of their real and imaginary parts, we directly plug in their Fourier decomposition in terms of the new creation and annihilation operators. Let's consider the first term first. We plug in the Fourier integrals and expand the product. Integrating over space reduces the complex exponentials to delta functions. If we then integrate over one of the spatial frequencies, we can substitute it with the other spatial frequency thanks to the delta functions. This is the expression we find for the first term. For the second term, we apply the same procedure. We plug in the Fourier expansions, expand the product, integrate over space to turn the complex exponentials into delta functions, and integrate over one spatial frequency to substitute it with the other spatial frequency. When we subtract the expressions we found for the two terms, we find that only the terms with the number operators remain. And so we find that this conserved quantity represents the difference between the numbers of these two types of particles. When we compare these expressions for the conserved quantities, we conclude the following about the two types of particles that correspond to the new creation and annihilation operators. The two particles have a property that we can call charge, and the two particles have opposite charge. The total charge is conserved, but the total number of particles is not. This is similar to Dirac's theory of holes, where pairs of particles can be created and annihilated, but charge is always conserved during these processes. However, the current result cannot be explained with the theory of holes, because the Klein-Gordon equation does not incorporate spin, so Pauli's exclusion principle does not hold. The two types of particles have momenta of the same sign, and more importantly, both types of particles have positive energy. This is a key characteristic of the theory of quantized fields compared to Dirac's theory of holes. Antiparticles are now considered particles with positive energy, and not holes in a sea of occupied negative energy states. We also consider the non-relativistic limit, in which the Klein-Gordon equation reduces to the Schrodinger equation. By defining a Schrodinger field and quantizing it, we can describe a system of multiple particles that satisfy the Schrodinger equation. We start by setting up the Lagrangian density. We can verify that the Euler-Lagrange equation yields the Schrodinger equation. When we calculate the Euler-Lagrange equation for the complex conjugate of the field, we find the complex conjugate of the Schrodinger equation. We can calculate the conjugate momentum of the field, which turns out to be equal to the complex conjugate of the field. The conjugate momentum of the complex conjugate of the field is equal to 0. We turn the field and momentum into operators by requiring that they satisfy the equal time commutation relation. Substituting the expression for the momentum, we find that the field and its complex conjugate satisfy an equal time commutation relation. To calculate the Hamiltonian density, we apply the Legendre transform and plug in the expressions for the momenta and the Lagrangian density. Now we will demonstrate that the Fourier coefficients of the field can be interpreted as annihilation operators. The definition of the creation operators then follows from taking the complex conjugate of the equation. Then, the annihilation operator can be written as the Fourier transform of the field. We can calculate the commutator of the annihilation and creation operator by plugging in the Fourier expansion of the field. We apply the equal time commutation relation, and when we perform the integrations, we find that the commutator equals 1 if the annihilation and creation operators are of the same spatial frequencies. This is the commutation relation that is indeed expected for annihilation and creation operators. We plug in the Fourier expansions in the expression for the Hamiltonian. Integrating over the spatial coordinate turns the complex exponential into a delta function, and if we then integrate over one spatial frequency, we can substitute it with the other. We obtain the number operator, multiplied with a factor that we can identify as the non-relativistic kinetic energy of a particle. Therefore, when we quantize the Schrodinger field, we find that each spatial frequency can contain a certain number of particles, and the total energy is given by summing the energies of all the particles of all spatial frequencies. Now, let's use Noether's theorem to find the conserved quantity that follows from the global phase symmetry of the Lagrangian density. We consider a small phase shift, so that we can define the additive change of the field. When we plug these results in the formula for the Noether charge density, we find that the charge density is proportional to the squared modulus of the wave function. So the conserved charge is the integral of the squared modulus of the field over all space. By plugging in the Fourier expansions for the field and its complex conjugate, we find that the total number of particles is conserved, as opposed to the relativistic case described by the Klein-Gordon field. We can obtain further insights by writing the fields in polar coordinates. Note that the amplitude of the field is the square root of the Noether charge density. We plug the expressions for the fields in the Lagrangian density and expand the products. To eliminate the square roots from the equation, we write the charge density as the square of its square root, and calculate its derivative by applying the chain rule. This result is plugged into the expression for the Lagrangian density. Now that we have expressed the Lagrangian density in terms of the squared amplitude and phase of the field, we can find the conjugate momentum of the phase variable. This turns out to be proportional to the squared amplitude variable. To make these variables quantum operators, we apply the equal time commutation relation. We substitute the expression for the momentum variable, and we divide out the factor of h bar. We can integrate both sides of this commutation relation over space, and recall that the integral of the Noether charge density over space gives the total number of particles. In this way, we find a commutation relation between the number of particles and the phase, which is very similar to the one that Dirac found using his method of second quantization. Now that we have quantized the real-valued scalar wave field, the complex-valued Klein-Gordon field, and the Schrodinger field, we will finally consider electromagnetic fields, classically described by Maxwell's equations. Electromagnetic radiation is especially important to quantize because that is where the development of quantum theory started. Einstein proposed that light consists of discrete particles, in spite of the overwhelming evidence that light is an electromagnetic wave that obeys Maxwell's equations. Now that we know how to quantize classical fields, we can finally resolve this paradox convincingly and straightforwardly. Or that's at least what one might think initially. But we will soon see that there are some subtle issues, the solutions to which are not entirely trivial. Before we start quantizing anything, let's first recap some classical theory of electromagnetism that we discussed in a previous video on special relativity. We saw that the three components of the electric field and the three components of the magnetic field can be put together in a quantity called the electromagnetic field tensor. With this quantity, we can transform the fields between reference frames more easily. We also saw that we can express the electric and magnetic field in terms of a scalar potential and a vector potential. By doing this, we can describe the fields with 4 degrees of freedom, instead of the 6 field components. Moreover, by writing the fields in terms of potentials, 2 of the Maxwell's equations are satisfied automatically. However, the potentials are not uniquely defined. Different choices of the potentials correspond to the same physical electromagnetic field. The degree of freedom that one has in defining the potentials is called the gauge, and one can switch between different choices of potential by applying gauge transformations. The potentials transform as a 4-vector, and the electromagnetic field tensor can be compactly expressed in terms of the potential 4-vector. In the following, we will express Maxwell's equations using the Lagrangian formalism, so that we can then quantize electromagnetic radiation. Note that since we consider freely propagating radiation, we consider Maxwell's equations in vacuum, so we set the source terms equal to 0. To express these equations using the Lagrangian formalism, we first express Maxwell's equations in terms of the electromagnetic field tensor, by taking the derivative of the field tensor. When we take the derivative of the field tensor, recall that we use Einstein notation, so we sum over the repeated index. So per column of the field tensor, we take the derivatives of the entries and sum over them. The first entry of the resulting vector we identify as the divergence of the electric field. The second term contains the x component of the curl of the magnetic field. The 2 other terms contain the y component and z component. We find that Maxwell's equations in vacuum are found by setting the derivative of the field tensor equal to 0. Now we will write a Lagrangian in terms of the field tensor, and demonstrate that Maxwell's equations follow from the Euler-Lagrange equation. The Lagrangian is given by the product of the field tensor with covariant indices and the field tensor with contravariant indices, which yields a Lorentz scalar. In Einstein notation, we sum over the repeated index. So in this case, we multiply each element and then add all the results. Therefore, the Lagrangian depends on the difference of the squared electric field and the squared magnetic field. We can collect some factors to simplify the expression. We can also express the Lagrangian in a different way, namely in terms of the potential 4-vector. When we plug in the expression for the field tensor in terms of the potential 4-vector, we can straightforwardly expand the product. We find that some terms are the same because we sum over repeated indices. Therefore, the indices are dummy indices, and swapping them yields the same result. So we collect those terms together. Now we find the equation of motion via the Euler-Lagrange equation. For one term we again swap the dummy indices to make it more transparent what happens when we take the derivative. We take the derivative and note that the result can be written in terms of the field tensor. Therefore, we found that this Lagrangian density indeed reproduces Maxwell's equations via the Euler-Lagrange equation. Knowing that we have found the correct Lagrangian density, we can now find the conjugate momenta which are necessary to quantize the field. The definition of the canonical momentum involves the time derivative which can be written as the zeroth component of the Fourier gradient. This allows us to easily take the derivative of the Lagrangian density. Note that we are essentially taking the derivative of a square, which introduces a factor of 2. We can identify the resulting expression as the zeroth row of the electromagnetic field tensor, which consists of the electric field components. Therefore, the conjugate momentum of the magnetic vector potential is the electric field vector, and the conjugate of the scalar potential is 0. With these results, we can calculate the Hamiltonian density. The Hamiltonian density is given by the Legendre transform of the Lagrangian density. Recall that also here we sum over repeated indices. Plugging in the results that we found, we obtain the dot product of the electric field vector with the time derivative of the magnetic vector potential. We can rewrite the latter in terms of the electric field and the gradient of the scalar potential. We saw previously that the Lagrangian density is given by the electric field squared minus the magnetic field squared. Plugging this into the expression for the Hamiltonian density gives the electric field squared plus the magnetic field squared plus the dot product of the electric field with the gradient of the scalar potential. The Hamiltonian is found by integrating over the Hamiltonian density. The integral over the last term vanishes, which follows from integration by parts and using the fact that the divergence of the electric field vanishes if no sources are present. Therefore, the Hamiltonian is found by integrating the squared electric field plus the squared magnetic field. Notice the relation between the Hamiltonian density and the Lagrangian density. The Lagrangian density contains the difference between the squared electric and magnetic field, while the Hamiltonian density contains the sum. This is similar to the case of a moving particle, where the Lagrangian is given by the difference of the kinetic and potential energy, while the Hamiltonian is given by the sum. Now we can quantize the field by applying the equal time canonical commutation relation to the conjugate variables. But when we plug in the expressions we found for these variables, we unfortunately run into some troublesome contradictions. For example, the commutator with 0 must always equal 0. But now we set it equal to a delta function, which can be non-zero. Also, the other three commutation relations contain a contradiction. To see this, let's take on both sides of the commutation relation the derivative with respect to the spatial coordinate where the electric field is evaluated. Since we consider the x-component of the electric field, we take the derivative with respect to the x-coordinate. We can add to this the y derivative of the y-component of the electric field and the z-component of the z-derivative of the electric field, because they both commute with the x-component of the magnetic vector potential. This gives the divergence of the electric field. But we know from Maxwell's equations that in the absence of sources, this divergence is equal to 0. And so we end up with the same contradiction, that the commutator, which is 0, is set equal to something that can be non-zero. To solve these contradictions, we will do two things. First, we will eliminate unphysical degrees of freedom by fixing the gauge. Recall that we started with 6 variables, namely the 3 components for both the electric field and the magnetic field. By writing them in terms of potentials, which automatically satisfy 2 Maxwell's equations, we have reduced the number of variables from 6 to 4. But ultimately, there are only 2 true degrees of freedom. For example, if we fix the x and y components of the electric field of a wave traveling in the z direction, then all other field components are fixed as well. Then, we will modify the commutation relations to take into account the fact that the divergence of the field vanishes. So first, let's fix the gauge. We write down Maxwell's equations in terms of the potentials if no sources are present. Now we will see how these equations simplify in the Coulomb gauge. The first equation is satisfied, and the second equation reduces to a vectorial wave equation for the magnetic vector potential. The electric field in this gauge is given by minus the time derivative of the magnetic vector potential. Since the vector potential satisfies the wave equation, we can write it as a sum of plane waves, which have different wavelengths and which propagate in all different directions. From the Coulomb gauge, it follows that this wave is transverse. That is, if we consider a plane wave that propagates in a certain direction, then the field vector must lie in the plane perpendicular to it. So we can define two basis vectors, psi and eta, that are perpendicular to any given wave vector k, and a basis vector zeta, which is parallel to k. We can write each plane wave component of the magnetic vector potential in terms of the psi and eta components, while the zeta component must be 0. The linear phase vector k.r can be written as the length of the wave vector k times zeta. It is important to keep in mind that the directions of psi, eta, and zeta depend on the direction of k, over which we integrate. Now we must write the Hamiltonian in terms of the magnetic vector potential and its conjugate momentum variable. The magnetic field is given by the curl of the vector potential, so we can calculate the magnetic field for a certain wave vector k by plugging in the expression for the Fourier component of the vector potential. We found that the momentum is given by the electric field vector. When we plug these results in the expression for the Hamiltonian and apply Parsifal's theorem to turn an integral over space into an integral over spatial frequencies, we have expressed the Hamiltonian in terms of the magnetic vector potential and its conjugate momentum. We can write the squared length of a vector as the sum of the squares of its psi and eta components, whose directions depend on the wave vector k. To quantize the Hamiltonian, we need to apply the commutation relations, but we saw previously that they suffered from contradictions. One contradiction is resolved because we work in the Coulomb gauge, where the scalar potential is 0, so it's not anymore a dynamical variable that should be quantized by imposing a commutation relation. To resolve the remaining contradictions, we apply the commutation relation in Fourier space. We saw what these commutation relations should look like when we quantize the scalar real-valued wave field. We also saw that the zeta component of a Fourier component of the magnetic vector potential is always 0, so this is not a dynamical variable that should be quantized. By applying the commutation relations this way in Fourier space, we have effectively modified the Fourier spectrum of the real space delta function to create a so-called transverse delta function, whose divergence is 0. We can now quantize the electromagnetic field. We define the annihilation and creator operators in the same way that we did for the scalar real-valued wave field. The prefactors in the definitions of these latter operators are chosen so that they match the prefactors in the Hamiltonian that we found. We calculate the commutator of the latter operators by using the commutator of the Fourier components of the vector potential and its conjugate momentum. The prefactor can be simplified by using the relation between the wave number, the angular frequency, and the speed of light. We find that the commutator of the latter operator equals 1, as it should. Recalling again how we quantized the scalar real-valued wave field, we can immediately write down the Hamiltonian in terms of the ladder operators. We can write the Fourier component of the magnetic vector potential in terms of the ladder operators and simplify the prefactor. Similarly, we can write the Fourier component of the conjugate momentum in terms of the ladder operators. One important result that can be derived from the quantized electromagnetic field is the spin of photons. Since spin is a form of angular momentum, we first find the total angular momentum of a classical electromagnetic field. This can be found by applying Noether's theorem to the rotational symmetry of the Lagrangian of the electromagnetic field. The resulting conserved quantity consists of two terms. By analogy with the angular momentum of an electron, we can interpret the total angular momentum as the sum of orbital angular momentum and spin angular momentum. In the case of electromagnetic radiation, the orbital angular momentum is related to the shape of the wavefronts. For example, if the wavefronts are planar, then the light propagates in a straight line, and there is no orbital angular momentum. If the wavefronts have a helical shape, then the light propagates in a corkscrew-like manner, and the field has orbital angular momentum. The spin angular momentum could be interpreted as one that is more intrinsic to the light, just like in the case of the spin angular momentum of an electron. Specifically, it refers to the polarization state of the light. For example, if the light is linearly polarized, then it has no intrinsic angular momentum. But if it is circularly polarized, then it does have intrinsic or spin angular momentum. When we quantize light, we will find that the intrinsic angular momentum due to the polarization state is the same as that of a spin-1 particle. To demonstrate this, we start by writing the expression for the spin angular momentum in terms of the magnetic vector potential and its conjugate momentum. To quantize this expression, we write the vectors as Fourier expansions with creation and annihilation operators, as we saw a moment ago. For each wave vector in the plane wave expansion, we define two basis vectors orthogonal to it. We saw that the field vectors must lie in the plane spanned by these two basis vectors. The third basis vector is parallel to the wave vector. When we plug in these Fourier expansions in the expression for the spin angular momentum, we obtain four terms of cross products, because we multiply two sums of the two basis vectors orthogonal to the wave vector. To simplify this expression, we integrate over the spatial coordinate to reduce the complex exponentials to delta functions, and then we integrate over one spatial frequency, which, thanks to the delta functions, we can set equal to the other spatial frequency. This expression can be further simplified by observing that the cross product of two parallel vectors vanishes. The cross product of the two orthogonal basis vectors yields the basis vector that is parallel to the wave vector. Switching the order of the multiplication yields a minus sign. Changing the sign of the wave vector changes the sign of the basis vector, so the cross product also gets a minus sign. If both the order of the multiplication is switched and the sign of the wave vector is changed, then the two minus signs cancel out. When we add the terms that contain the multiplication of two annihilation operators, we obtain a function that is antisymmetric. Also, the sum of the terms containing the multiplication of two creation operators yields an antisymmetric function. Therefore, the integral over these terms vanishes. We can simplify by collecting terms, because the operators corresponding to the different components psi and eta commute with each other. We now introduce new ladder operators, which are linear combinations of the ladder operators of the two different components. We denote them with the subscripts L and R, because we will see that they correspond to left and right circularly polarized light. We can verify that these new ladder operators indeed satisfy the commutation relations that proper ladder operators should satisfy. We can express the new number operators in terms of the old ladder operators. When we subtract the two new number operators, only the cross terms remain. The resulting expression matches the integrand of the spin angular momentum integral. So when we plug in this result, we find that the spin angular momentum is given by the reduced Planck's constant h bar times the number of left circularly polarized photons minus the number of right circularly polarized photons. To see why these new ladder operators indeed correspond to left and right circularly polarized light, we recall the theory of Jones vectors in classical optics. The two components of the Jones vector describe the complex amplitudes of the electric field vector in the plane that is perpendicular to the propagation direction of the light. When these time-independent, complex-valued amplitudes are converted to physical time-dependent, real-valued field components, we find that the field vector traces out a circle. We therefore say that the light is circularly polarized. If we change the sign of one of the components, the circle is traced out in the opposite direction. Therefore, we conclude that each left circularly polarized photon carries an angular momentum of positive h bar, while each right circularly polarized photon carries an angular momentum of negative h bar. In either case, the angular momentum vector is in the zeta direction, which is parallel to the propagation direction of the light. This property is reminiscent of spin-1 particles, who have a spin vector of length 1 and whose projection along the z or zeta axis can be -1, 0, or 1. So we infer that photons are spin-1 particles. However, a zeta projection of 0 is not allowed for photons because light is a transverse wave. That is, if a plane wave propagates in a certain direction, then the electric field vector is perpendicular to it, as long as the angular momentum vector is parallel to the propagation direction, or antiparallel. However, if the projection along the zeta direction is 0, it means that the field vector can be parallel to the propagation direction, which is not allowed for a transverse wave. This result is consistent with a selection rule that was already known from Heisenberg's matrix mechanics. We found that an electron can only transition between states where its angular momentum in the z direction changes by at most 1 quantum. If the z component of angular momentum changes by 1 quantum, then the emitted light quantum is circularly polarized. We just found that a circularly polarized photon has 1 quantum of angular momentum, so this is consistent with conservation of angular momentum.